Dr. Courtney with the Quantitative Reasoning Center. Practice is important in mathematics, just as it is in music. The task at hand in this problem is to find the center of mass of a cube, and the cube extends in the x, y, and z directions from 0 to a, and it has a density given by x squared plus y squared plus z squared. So the big idea, the interpretation, is that we need to use triple integrals over the given volume to find the mass, as well as to find the x, the y, and the z components, or coordinates of the center of mass. So that's what we mean by the x with the line over it, the x coordinate of the center of mass, the y coordinate of the center of mass, and the z coordinate of the center of mass. So by definition, the mass is the triple integral of the density, and this is over dx, dy, dz. So the x coordinate goes from 0 to a, the y coordinate from 0 to a, and the z coordinate from 0 to a. And the coordinates of the center of mass are computed with similar integrals. But let's kind of draw a picture to help get our mind around what's going on as part of our develop stage. And usually we make, when we draw a three-dimensional coordinate axis, usually that's y, this is x, this is z. So we go from 0 to a in x, 0 to a in y, and 0 to a in z, so that our cube that we're really integrating over ends up looking something like this in three-dimensional space. Alright, so for our plan, we want to express the mass integral, and we've already done that, and then we want to express, and actually we do have to compute the mass integral first. In other words, evaluate that integral, and we're going to do that in Matlab. And as we'll see in a minute, Matlab is very powerful and nifty for computing these multivariable integrals. And then we want to express each coordinate integral, and then we compute each coordinate integral. So we lather, rinse, and repeat for the y and z coordinates. Alright, so we've already got our mass integral, and of course we're going to substitute in our expression for the density each time. And then the coordinate integrals, the x coordinate of the center of mass is a triple integral, and of course the region of integration is the same. And it's the integral of 1 over the mass times x times the density, and then of course over dx, dy, and dz. And then the y coordinate is a very similar looking integral, except it has the y coordinate slip in here, and likewise for the z coordinate of the center of mass. So we've set this up about as much as we can in with pencil and paper. So we're going to use Matlab to do most of the evaluation step. And then let's think about, what are we expecting with the assessment step? Well, we're expecting the mass probably to be proportional to the size. Well, actually, you think you're integrating over something squared, and then it's a three-dimensional integral, so that's going to tend to give you 3 more powers of a, so the mass is probably going to be proportional to a to the 5th power. And then each one of the coordinates, x, y, and z, because of symmetry, will actually compute all 3 integrals. But because of symmetry, we're expecting them to be the same. And we're also kind of expecting them to be, where's the middle of this cube? You do have, well actually we don't have a great symmetry going on here, because as you get further away from the origin, you become more dense. So they're all going to be equal to each other, but we're not really expecting them to be right at the center of the cube. We're probably expecting them to be close to this corner here. So somewhere between a over 2 and a. Because if the x coordinate is bigger than a, then your center of mass is not even in the cube anymore. And because of the symmetry of the situation, we're really not expecting that to happen. So we're expecting the coordinates of the center of mass to be between a over 2 and a, and we're expecting the mass to be proportional to a to the 5th power. Alright, here we are. We got Matlab up and going. And first thing we want to do is we want to hit it with a sims x, y, z real to define all our variables. And then we can go ahead and compute the inside integral, and this is for the mass now, as the integral of the integrand, which is x squared plus y squared plus z squared, which is the density, over the variable x from 0 to 2. Actually, we might be able to do this over a. Let's go ahead and make a real variable, but then we just won't integrate over it. This might work. Let's try going 0 to a. Hey, looks like we're working so far. And now the middle integral is going to be the integral of the inside integral over the variable y from 0 to a. And now the outside integral, which is the same as the mass, is going to be the integral of the middle integral over the variable z from 0 to a. So, as we thought, m, the mass, is equal to the outside integral. It's equal to a to the 5th power. And we were really just expecting it to be proportional to a to the 5th power, but it actually ended up turning out to be exactly equal to a to the 5th power. Okay, I was flailing about a little bit and I was making the syntax error of forgetting to type the in command. So the command we wanted for the inside integral computing x bar is the integral of x times the density over m over the variable x from 0 to a. And now we can continue computing now the middle integral. And that's the integral of the inside integral over the variable y, and the limits of integration are still 0 to a. And now the outside integral, which we'll just go ahead and call x bar, because it's the x coordinate of the center of mass, is the integral over the middle integral. The variable now is z, and we're going from 0 to a. And we get 7a over 12. And we can ask ourselves, does this make sense? Yes, it does, because we were expecting something to be between a over 2 and a, and 7/12 a is in the range that we had expected. And now we can repeat this, working with the variable y, but the integrand here is still x, so now we're computing the inside integral for y bar. And now the middle integral is the integral of the inside integral over y from 0 to a, and now x bar, we want y bar, and once again, as expected, the x and y components of the center of mass are the same. And now we can go ahead and compute the integral, the inside integral for the z component, or the z coordinate of the center of mass, compute the middle integral, and now compute z bar. So the coordinates of the center of mass are all 7a over 12, which is in agreement with what we were expecting. So our assessment shows that our answer does indeed make sense.